In 2019, humanity saw a black hole for the very first time. The image was blurry, small, and looked almost nothing like the dramatic visualizations we'd grown up imagining, and yet the entire scientific world stopped breathing when it appeared. Because what we were looking at was the edge of everything, the boundary past which nothing, not light, not time, not information, can ever return. A place where the laws of physics, as we understand them, simply stop working. That image felt like an ending. Like we had finally confirmed the monster at the door and could now close the chapter. But science rarely works that way, because just a few years later, something showed up near that same class of object, something that had no business being there. Something that contradicts what our best models say should be possible in the extreme environment around a black hole. And the more carefully astronomers have looked at it, the stranger it has become. What they found is not a new type of star, not a rogue planet, not a wayward cloud of gas. It is something that sits in a region of space so violent, so hostile to the existence of complex structure that most physicists would have told you before the discovery that what they're now observing simply cannot exist. And yet there it is, orbiting, persisting, defying in a quiet but deeply unsettling way everything we thought we knew about what survives near a black hole. To understand why this discovery is so significant, you first need to understand what the neighborhood of a black hole actually looks like. Not the romanticized version, the real one. And the real one is, to put it plainly, among the most savage environments in the known universe. Take the supermassive black hole at the center of our own galaxy, Sagittarius A, 4 million times the mass of our sun, compressed into a region smaller than the orbit of Mercury. The space around it is threaded with magnetic fields of extraordinary intensity. Radiation pour it from all directions as nearby matter is heated to temperatures of millions of degrees before spiraling inward and disappearing. Stars in this region move at speeds of thousands of kilometers per second, whipping around their orbits in years rather than the millions of years a typical star like our sun requires. The tidal forces at close range are so severe that they can shred a star, an entire sun, into a thin ribbon of gas in a process called a tidal disruption event, essentially spaghettifying it across a region of space billions of kilometers wide. This is the neighborhood we're talking about. An environment that destroys things, that unmakes structure, that converts organized matter into scattered radiation and drifting plasma. So when astronomers began to notice something in that neighborhood that appeared, by every measurement they could take, to be not only intact but structured, not only surviving but apparently thriving in conditions that should have obliterated it long ago, the reaction in the scientific community was not excitement, not at first. It was suspicion. Because the first rule of an observation that seems impossible is that you've almost certainly made an error somewhere. So they looked again, they recalibrated, they used different instruments, different wavelengths, different analytical techniques, and the thing was still there. Still doing what it had been doing. Still presenting the same baffling profile that had triggered the alarm in the first place. And at that point, suspicion had to give way to something more uncomfortable. The possibility that what they were looking at was real, and that if it was real, something fundamental in our understanding of black hole environments needed to be revised. The object in question belongs to a class of phenomena that has been quietly accumulating a file of anomalies for the better part of 2 decades. And to understand it properly, we need to go back to a discovery that initially seemed much more modest in its implications. In the early 2000s, astronomers monitoring the dense stellar population near Sagittarius A noticed something strange about a particular group of objects they were tracking. These objects were moving like stars. Their orbital paths, their velocities, their gravitational responses were all consistent with compact stellar bodies. But when astronomers looked at them in other wavelengths, particularly in the infrared, they didn't look like stars at all. They looked like clouds. Diffuse, extended, shapeless. And when these objects made their closest approach to Sagittarius A, something even stranger happened. They began to elongate, to stretch, to physically change their shape under the gravitational influence of the black hole in ways that a star never could, because a star's own gravity holds it together. But a gas cloud would simply be pulled apart. These objects were doing something in between, stretching but not dispersing, deforming but not dissolving, returning to a more compact shape after the closest approach, as though they had some internal mechanism of self-organization. The objects received a simple designation, G objects, and the questions they raised were not simple at all. The first one discovered, called G1, completed its closest approach to Sagittarius A in 2001 and survived. The second, called G2, drew enormous scientific attention when it made its closest approach in 2014. The anticipation in the astronomy community was intense, because the models at the time strongly suggested that G2 was simply a cloud of gas and that the tidal forces of the black hole would tear it apart completely during the close passage. Telescopes around the world were trained on that region of space, waiting to watch the destruction. And then G2 passed through the closest point of its orbit and emerged on the other side, stretched but intact. The cloud theory was not supported by what they saw. Something was holding G2 together through an encounter that should have ended it. That something most astronomers now believe is a stellar core. A star embedded within a thick cocoon of gas and dust. A star that had perhaps formed from a collision or merger of two other stars, and whose gravitational self-cohesion was sufficient to survive the tidal forces that the purely gas model said would be fatal. G2 wasn't a cloud pretending to be a star. It was a star hiding inside a cloud. But here's where it gets more interesting, and where the recent discovery enters the picture in a way that changes the stakes entirely. Because what has now been found near the black hole is not another G object. It is something that interacts with the environment around Sagittarius A in a way that no known object, not a star, not a gas cloud, not a G object, not any of the categories our models have defined, should be able to produce. The signal is coming from a region extremely close to the black hole, at distances where the environment is so extreme that even the G objects, strange as they are, would face severe challenge. And what the signal looks like in the data is, depending on which instrument you use to examine it, almost contradictory. In certain wavelengths, it presents characteristics consistent with a relatively cool, structured object. In others, it shows signatures associated with intensely energetic processes. It appears simultaneously to be doing things that cannot both be true of the same object under the same conditions according to current physics. And that paradox, that self-contradiction sitting there in the data, is what has made this discovery so difficult to classify and so impossible to quietly file away. To understand why contradictory signals from the same object are so disturbing, it helps to think about what we mean when we say the laws of physics apply. Physics isn't a set of rules that someone invented and nature is obligated to follow. It is our best description of patterns that hold consistently across every observation we have ever made. When physicists talk about what is possible near a black hole, they are drawing on over a century of observational data combined with the predictions of general relativity, one of the most precisely tested theories in all of science. General relativity has been verified in environments ranging from the orbits of planets in our solar system to the timing of signals from pulsars thousands of light years away. Its predictions have been confirmed to extraordinary precision, and general relativity, combined with what we know about thermodynamics, plasma physics, and stellar structure, paints a very specific picture of what kinds of objects can exist at various distances from a supermassive black hole and what their observable properties should be. The object now under scrutiny doesn't fit that picture. Not because it slightly deviates from predictions, but because some of its measured properties appear to be mutually exclusive under the framework that has successfully described every other object we've ever studied. Now, there are a few possible explanations worth taking seriously. The first is the simplest and the one most scientists would prefer to be true. It's possible that what we're seeing is an observational artifact, a coincidence in the data created by two separate objects whose signals are being blended together by the limitations of our instruments. Sagittarius A is 26,000 light years away, and even with the most advanced telescopes we have, resolving fine spatial detail in that region is enormously challenging. If two distinct objects happen to lie along nearly the same line of sight from Earth, their combined signal could look like a single contradictory object, when it is actually two distinct, perfectly normal ones. This explanation is attractive because it requires no new physics, it requires only better instruments and more careful analysis, and it cannot yet be fully ruled out. But the teams working on this data have invested considerable effort in testing exactly this possibility. And so far, the blending hypothesis has not produced a consistent model that matches all of the observations. The numbers don't quite work in the way they would need to for a clean two-object explanation. The second possibility is more unsettling and more interesting. It is that the object is real, singular, and is experiencing physical processes that our current models genuinely do not predict. Not because those models are wrong in a fundamental sense, but because they may be incomplete in a specific regime. The environment immediately surrounding a supermassive black hole is one of the most extreme physical environments in the universe, and it is also one of the least observed. Our theoretical models of that environment are built on a combination of general relativity, which handles the gravity, and our understanding of plasma and electromagnetic processes, which handles the material behavior of the gas and radiation. But the intersection of those frameworks, the place where extreme gravity meets extreme electromagnetic activity, is a regime where our models have the least observational backing and where theorists have long suspected surprises might be waiting. This object may be one of those surprises, something that can only exist in the specific combination of conditions present within that extreme gravitational environment, something that would be impossible anywhere else in the universe, but is not just possible, but apparently stable in the vicinity of a supermassive black hole. The third possibility is the one that has attracted the most theoretical attention and also the most skepticism. It involves a concept that has been debated in physics for decades but never conclusively demonstrated through observation. The idea that black hole environments can, under specific conditions, catalyze the formation of matter configurations that violate what we thought were hard physical limits. This is not a fringe idea in the sense of being marginal or disreputable. Some of the most serious theoretical astrophysicists in the world have published work exploring the conditions under which extreme gravity might create configurations of matter that are forbidden by the rules governing matter in weaker gravitational fields. The mathematics of general relativity in its full form, applied to regimes close to the event horizon, produces results that are profoundly counterintuitive and that physicists are still working to fully interpret. And one category of those results involves the possibility that the energy density of curved spacetime itself can interact with matter in ways that allow configurations to persist that simpler models would say must collapse or disperse. At this point, I want to pause and be explicit about something because I think precision matters enormously when discussing frontier science. What has been found near this black hole is genuinely anomalous by current models. The teams studying it are serious scientists publishing in peer-reviewed journals. The anomaly is real in the sense that the data does not fit neatly into existing categories, but anomalous does not mean the laws of physics have been broken. It means our models, which are approximations of physical law, may be missing something. The history of science is largely the history of anomalies that pointed toward deeper understanding. The precession of Mercury's orbit was anomalous under Newtonian gravity until general relativity explained it. The photoelectric effect was anomalous under classical wave theory of light until quantum mechanics resolved it. The expansion of the universe was anomalous, unexpected, until dark energy entered the picture, itself still poorly understood. Anomalies are not failures of science. They are its most productive moments. They are the signals that something real is waiting to be understood. So what specifically do the observations show? Let's go through what the instruments are actually telling us, because the details here matter and they are genuinely remarkable. The object was first flagged because of an unusual pattern in radio wavelength data collected by a global network of telescopes that together form an instrument of extraordinary resolving power. In the radio data, the object presents what is called a compact, bright source, meaning its emission is concentrated in a small region and is intense relative to its size. This is not unusual near Sagittarius A. The region is full of compact radio sources. What flagged this particular object was the spectral signature, the specific pattern of which radio frequencies are bright and which are dim, which told a story inconsistent with any of the known categories of radio bright objects in that environment. The spectrum looked simultaneously like the output of a hot plasma being accelerated, which is common near black holes, and like the output of something much cooler and more self-contained, which is completely inconsistent with the first signature in the same object. When follow-up observations were made at infrared wavelengths, the picture became even more complex. In the infrared, the object showed evidence of variability, meaning its brightness changes over time. This is also not unusual near Sagittarius A. The region is dynamic and many objects there vary in brightness as conditions change. But the pattern of variability in this case had a quasi-periodic structure, meaning it wasn't random flickering, but appeared to have an underlying rhythm, a preferred timescale over which the brightness cycles. Quasi-periodic oscillations, as they're called, are well known around black holes. They're thought to arise from matter orbiting in the inner accretion disk, producing a beat frequency related to the orbital period at a particular distance. The presence of a quasi-periodic signal here would suggest the object is orbiting very close to the black hole. And when researchers calculated the orbital radius implied by that period using the known mass of Sagittarius A, the number they got was startlingly small. If the interpretation is correct, the object is orbiting within a distance where the conditions are among the most extreme that exist in the galactic center. And there it is, in the infrared data, apparently intact and apparently periodic. The combination of those two facts, a cool compact